So that wasn't recorded, haha. Yeah, so you can ask me anything, anything as we go along. Okay, so we'll work through the exam format back to front. So in the reverse order, starting with the sort of most recent material and then and working back to older material. So the exam's going to be 50 multiple choice questions. So exactly twice as long as the midterm exam. You'll have 2 hours to do it. That's nice. We'll all be out of there after 2 hours. 25 questions from the post-midterm material and 25 questions from pre-midterm material. So about half and half split from stuff we did before and after the midterm, or rather, I should say 24 pre-midterm and 1 bonus question. There's very little you can do to prepare for the bonus question, but the exam will only be out of 49, so it really is a bonus question. Here's the topics. So 9 questions will be about Java. And that's mostly about comparing Python and Java. So those will be questions like, here is something in Java, what's the equivalent thing in Python? Or here's something in Python, what is the equivalent thing in Java? Nothing too complicated there. Maybe also focusing a little bit on some of the differences between Python and Java. So maybe there is no equivalent thing in Python, or maybe it just doesn't make sense in Python, or it doesn't make sense in Java. So there'll be stuff about that. So anybody like to ask me a question about Java? Yep.
So would it be like if you said like if the Python has a function, it's like the equivalent of function in other 2 methods?
Yeah, so it might be something like, you know, Python has a list class. What's the equivalent thing in Java? Or, you know, Java has arrays. Is there an equivalent thing in Python? So that kind of question. But keeping in mind that these are multiple choice questions, so you might, you know, there might be more than one answer, but there won't really be more than one answer that's available to you on the exam. Yeah?
Could it be a mathematical function that doesn't necessarily equal the same thing in either Python?
Yeah, that could be a fair kind of thing. Like, for instance, you know, 3 divided by 2. That gives different results in Java and Python. One of them does integer division, the other one does floating point division. Yep.
When we do, like when we're doing division, are we considering that doing before the
Yeah, so I think that's explicit on the header of the exam. The Python code is always running under -q new or from future import division, so that when you do divisions, you get real division. If you want integer division, it's the 2 slashes, the div operator. Any other Java type questions? Yep.
So Java doesn't do integer division by default?
Java does do integer division by default. If you give it, no. Python does floating point division by default. Oh, sorry, by default meaning newer versions of Python, if you divide one number by another, you get a floating point result. Java, if you take an integer and divide it by another integer, you get an integer. Any other Clarifications, questions? Okay, good. There will be 9 questions about analysis of algorithms and analysis of recursion. So these will be questions like, here's a recursive function. If I call it with these arguments, what's the recursion depth? Or here's a recursive function. If I call it with these arguments, what is the running time look like? So, you know, things to look out for, questions like this. What is the running time of this function with when n is equal to about 10,000? 10,000 is a number that I like to use a lot for these things because often that separates really bad algorithms from decent algorithms. And when I say running time, that will typically be asking about a very specific thing, like here's the code, how many times does line 4 of this code execute if you run this with on an array of length 10,000. So know how to do things like understand what happens when you have 2 nested loops, you know, each of which runs over all 10,000 elements. How often does that intersection of code execute? We'll also want to look at things like if you have a recursive function, you know, being able to draw out the recursion tree and reason about the number of times, number of calls to the recursive function. Another example question is what is the recursion depth of this function? So with a specific argument given to it. So again, that's drawing this recursion diagrams, these stack frames as they pile up, and checking to see how many stack frames you ever have at any given point in time. So remember, if they're simple recursive functions where the function just calls itself once, that's a pretty easy thing to do. You get a bunch of stack frames that just pile up on each other until you get down to the base case, and then they all return. So the number of those stack frames gives you the recursion depth. If it calls itself more than once, then you end up with these recursion trees where you have, you know, there's the root of this thing which calls itself recursively, which then calls itself recursively, and so on. But then as you come back up, this, you know, if it calls itself twice, you end up with each of those things having 2 recursive calls. You end up with this giant binary tree. So for example, a recursion depth of, if you have something whose recursion depth is 10, and it's a simple one that only calls itself once, it's easy to draw that out. It only has 10 stack frames. If you have something whose recursion depth is 10, but it calls itself twice, and on problems of the same size, then that would be hard to draw because it would have about 1,000 nodes inside of it. So a little bit more than 1,000 nodes. So that would be not something I would expect you to draw. If you find yourself making a picture while trying to solve something that has 10,000 nodes, it's time to start thinking at a higher level. So thinking about, just figure out what the depth is, and then you can maybe figure out the size of the tree. One thing that will be important is to remember what log n is. And it's the number of times we can divide n by 2 before getting a result less than 1. And log of 10,000, that's actually about, it's between 13 and 14, so we can settle on it being roughly 14 if you need to do that. And then the powers of 2, important ones are log of 256, what's that? 8. And the log of 8? 3. Okay. Yeah, so practice drawing these recursion trees and analyzing these recursive functions. This is a really important thing to learn. You'll learn to do this more and more as you progress in computer science. But if you ever intend to use recursion, you sort of have to be able to do this. Otherwise, it's really easy to write recursive functions that basically, for large values of n and not even such large values, for like n equals 100, they will behave like they're never ending. They'll behave like infinite loops because they'll take something like 2 to the 100 steps to execute, which is more time than anybody has to wait. Okay. So, good time now to ask me a question about anything to do with analysis of algorithms or recursion. Yeah? Is this going to be what? Yes, it's already in that that directory. It'll show up within the next hour. Yeah? No, there won't be a practice exam. More useful for you if you go through this this breakdown of these questions and make up your own questions like this. Post them on the forums, solve them, do whatever, share them as much as you like. That will have you thinking about it more than just a practice exam where you knock off a few questions that are exactly the ones on the practice exam. So we had a practice exam for the midterm, which was, quite close to the actual midterm, and that didn't really help much. So the median on the midterm was still about 60, I think it was 66%. So doing an exam that's a lot like the one you're going to do doesn't really help. You need to know a lot more around, a lot more stuff than exactly what's on one exam. This is a better way to do it. So any other? This is the toughest part of this thing. I guarantee that these are the questions that people will do the worst on. So practice these things. You're looking at 9 out of 50 questions here, so it's not a small part of the exam. Okay. All right. You'll have 10 questions. Sets, dictionaries, arrays, and/or binary search. Okay? So, things to remember. Sets and dictionaries can look up values in constant time. Doesn't matter how big the set or dictionary is, you can look for any value in that set or dictionary in constant time. And this has an important limitation associated with it. If some value is not in there, then all you learn, then that's all you learn. Okay? So if some value is not in the set or dictionary, the only thing you can learn about that from the set or dictionary is it's not there. Okay. So that's important. That differs from something like binary search, doesn't run quite as fast. It runs in order log n time, so it has to look at log n different values in your sorted array. But what do you learn from binary search? If you do binary search and at the end of this thing you don't find what you're looking for, do you learn any useful information? Something that could be useful to you? No? So, I mean, here's here's a sorted array. We could do binary search on this. And I could ask you to search for the value 17. So 17 is not in that array, so binary search won't find it there. But what useful, maybe useful information does binary search tell you? So where will binary search finish and tell you that it's not there? At the end? No, binary search will never look at the last element of the array if you're searching for 17. Yeah?
It'll end where 17 would be?
Yeah. So binary search will start at the middle and repeatedly narrow the range down by a factor of 2 each time until it's narrowed it down to an array of length 1, which is where 17 would go if it was in the array. So binary search will finish off here and say, look, here's where I finished. 17 should go here, but it's not there. So I conclude that 17 is not in the array. But I also conclude that, the closest thing in the array that's bigger than 17 is 23. And if I just look back one position, then the largest thing that's smaller than 17 is 15. So I know exactly what 17 is between, what two values it's in between. And that can be really useful information, right? So maybe you weren't looking really for 17, you were just looking for the closest thing, or maybe what you're going to do is somehow insert it this way. So that's a really useful piece of information. So, so if you search for something that's not in the sorted array, you learn where it would go. So this is actually something that's fairly important difference between things like binary search and things like sets and dictionaries. If you never care about things that you don't find, so if you don't care where they would go, then you should never be using something like binary search or binary search trees that you'll learn about in other courses. If all you care about is finding it if it's there and telling me if it's not there, then sets and dictionaries are the data structures that you should use. They're faster. They can do that faster than binary search, and if they do what you want, then that's what you should use. This is something that I have to hammer into my data structure students in second year, and it's something that is a common misunderstanding in basically even in people who have programmed for many years. You find them using binary search when there's a better alternative, which is something like a set or a dictionary or whatever the equivalent is in their language. Okay. We will have 4 questions on object-oriented programming in Python. So classes and objects that you create from these classes, and you know exactly what happens there. So, you know, expect a little class hierarchy with a, you know, base class and some subclasses. So where you have something like the person class and then the musician, which is a kind of person, or the employee, which is a kind of person. And knowing, you know, if I make a musician and I call its string function, what exactly gets executed? Where is that function defined? Is it defined up in the person class, or is it defined down in the musician class? That sort of thing. And again, because it's something that breaks a lot of programs in practice, what happens when you override equal, and why that means you should override hash. Okay. And the rule here is if you redefine equal, you should also redefine hash. Otherwise, you can't put your objects into sets or dictionaries. Okay. So that's a hard lesson to learn, but it's something that, you know, you'll be taught this again when you take data structures, the dangers of this kind of thing. And there's related dangers which we didn't look at too much that have to do with changing things, modifying objects that are in a set or a dictionary. Okay. Any questions for me? This is your chance. It's your last chance. Yeah.
Do you mind going over what a hash was?
Okay. So, let's define a little class that'll, I don't know, store some value. Let's call it foo, and say self.foo equals foo. So when we create one of these things, it'll have a property called foo that you specify when you create it. And I'll say that this thing is equal to another thing if self.foo is equal to the other things.foo. Okay? So right now we're in a bad state. This is not a great class. If I, oops. I've really forgotten all my Python.
These recurs that self.foo equals other.foo.
Jeez, full of bugs. Okay, so so does A equal B here? No, because A's foo is ha and B's foo is ho. So those two are not equal, but I can create a new C whose foo is also ha, and A equals C. So far, so good. But what if I make a set with A and C? Now, this set Should it contain 2 elements or 1? Yeah. It should only contain 1 because A and C are equal and the elements inside a set are not supposed to be equal. Now I don't really know what's going to happen here, but I can try it and see. And actually what I find is this thing contains actually 2 elements. It contains a myClass object at that location, and it contains another myClass object at that location. And those myClass objects are the objects A and C. So it's not behaving as it should here. Okay? So the reason it's not behaving as it should is that sets, when they store things, they hash them, and they use that hash value to determine where inside some array those values should go. And the hash value has to be such that if 2 things are equal, they get stored at the same location, so the set knows not to put 2 of them at that location. So the fix is to define a hash function for our object that only considers the stuff that we care about being equal. In this case, the foo property is the only thing that matters to test if two of our objects are equal. So what we should return is the hash of self.foo. Okay? So if I look now, if I hash A, I get some number, and if I hash C, I get some other number, and I really should be getting the same number for those 2 things if they're equal. So let's try it with this modified class. If I hash A, I get that. And if I hash C, oh, sorry, C should also be a ha. And if I hash C, I get the same value as hashing A, right? So now they have the same hash. When I try and put them into the set's going to use those hashes to determine where they should go. And when it tries to put the second one in, it's going to be trying to put it at the same place. It's going to try and put C at the same place as A. And it's just going to realize that it shouldn't have those 2 elements in the set. So I just get 1 object in the set that way. Okay? But of course I can make B which does have this different hash value. And if I make a set that has A, B, and C in it, I get 2 values in the set. A and B are the 2 values that get in there. C never made it because it's already equal to something in the set A. Yep.
What if you change B's foo to ha as well?
Aha. So now you get into this issue that you should never change things which are in a set. So I can do that. B.foo equals ha. Now that set, well, the set that I created, but I've lost it now because I never saved it, still has those 2 elements in it, both A and B, which are equal. So you're not supposed to modify things in the set if it could change the result of the equals method. So that original set is now broken because it has 2 equal elements in it. You're not supposed to do that. And a good strategy for that is to make classes where it's not expected for you to change the values of the variables in the class if you want to put them in sets. Okay. So so that, changing the values of variables inside of properties of things that are inside a set is generally a bad idea. Yeah.
When you do the if one thing is another thing, like if the hash value is the same, would they consider it?
No. So is basically just looks at the place in memory where these things are stored. And so here we have A, B, and C. And when you don't create a string thing like this, you can actually see where these are stored. A is stored at this location, the memory address that ends with a 50. B is stored at this address that ends with a 90. And C is stored at this address that ends with a A50, not the 950 that A is at. So they're all at different locations. So if I say A is C, I get false, even though A equals C and hash of A equals hash of C. It still cares, the is operator still cares only about the address of these things in memory. And that matters because is will tell me if I change something inside of A, is that also changing something inside of C? And the answer is no, because they're in different places in memory. Yep.
So the hashing doesn't change the place of your memory, right?
No, hashing just changes what is returned when you hash this object. And here, it's basically always the case that there's a nice recipe, which is you just look at the equals method, check to see what it equals is using to determine if two things are equal, and those are the things you should hash. And luckily, hashing, so we can, if we had two things, bar equals bar, so if we had an object with two parts, foo and bar, maybe they're only equal if both the foo parts and the bar parts are equal. Then to hash them, you'd want to hash both those things. And luckily, you can hash tuples. So you just do something like that. Super easy. And sometimes it's not exactly the properties that you hash. It's whatever equals is using to compare. So maybe this doesn't care about case. So it might convert them to lowercase before comparing them, in which case you would do the same thing for the parts that are converted to lowercase. So take all the stuff that's used to test equality and hash all that together. That's the recipe. Okay. Any more questions about that? And if you don't do that, if you fail to do this hashing thing, then the results are unpredictable. It doesn't look like it here because we keep ending up with both objects in the set, but that's highly dependent on the implementation and exactly what happens with the different hash values. There's still a chance that, in fact, a decent chance that you may get only one of the elements in the set, or you may get both of the elements in the set. You never can really be sure. Okay. There will be 3 questions. Arrays, lists, and what do we call it? Aliasing. Aliasing is this A is B versus A equals B. So aliasing is what happens when you say you create some array A and you say B equals A. Then it's called aliasing because A and B are both aliases for the same array in memory. So that it's just 2 different names for the same thing. If you change A, you're changing B. So remember those pictures that we drew that have little boxes representing the names of variables, and then those boxes have arrows pointing off to things in memory. And be able to know that when you do an assignment operation like A equals B, all you're doing is taking that box for A and having it refer to the same thing that B refers to. And sometimes that matters a lot, like if they're referring to an array, because you can change an array, in which case you're changing them both. Sometimes it doesn't matter at all, because, for instance, A could be referring to an integer, in which case, if you make B refer to that integer, that doesn't really matter because you can't actually change the integer. All you can do is have A refer to something else or B refer to something else, but you can't change the value of the integer in memory, unlike in arrays. So integers are what's called immutable. Okay. So that I think you guys know pretty well. And then there will be 12 questions on the programming basics. Things like, what does this code return? What does this code evaluate to? Generally, what does this code do? Or what is this code doing? Okay. So that's, going right back to things like simple arithmetic expressions to know, make sure you understand how those things work. Things like order of operations, precedence, and so on. Okay. So any questions? This is it. I have nothing else for you, so the only way that we'll continue here is if you ask questions. If you don't, then we're done for the day and for the semester. Okay, yeah.
Why does it say more not pig mode?
Why does it say what?
More not pig mode.
More where? Sorry, I didn't hear what you said. More on that. Oh, pig dog. It's just the name of my computer. Yeah, I like to take two random German words and concatenate them to make my to name my machines. Yeah, so the Germans know that. Okay, I guess you've been looking at that all semester, wondering. All right, going once, going twice, gone. So I'll see you in 9 days or so. Good luck.